Hello, I'm Anna Mackay and we're looking at logarithms in base 10. So what do we mean by base 10? If we have the function y is equal to 10 to the power of x, so we have a base of 10 here and x is in the power. First question here, when y is 10, what is x equal to? So you could look along the axis here and see when y is 10, what would be x equal to? 1. Let's think about that. Because we're saying 10 raised to the power of what number would give you 10? So that would have to be 10 raised to the power of 1 to give you 10. What about if y was 20? So from the graph that we can see, if y was 20, let's come along and see what our x-coordinate would be. And so what we're saying here is 10 raised to the power of what gives you 20? So we've ascertained that 10 to the power of 1 gives you 10. 10 to the power of 2 would give you 100. So 10 to the power of what number would give us 20? Well, it has to be somewhere between 1 and 2 and on the lower side that you'd like to think. So we're not getting very exact numbers here. As in what I mean is that we would need the equation of that to give us exact numbers. So what is this logarithm or log concept, as we tend to abbreviate it to? So in this situation, we're saying that x is the logarithm in base 10 of y. I'll write that down. So what we're saying is that the logarithm in base 10 is, and this is how we write it here, you see log and base 10, of a positive number is the power that 10 must be raised to in order to obtain that number. This will make a bit more sense as we keep going on, and I'll keep coming back to this idea. So what we write here is the log base 10 of 20 is equal to 1.3. I'm going to be talking about a bit of a flowchart on and on and on when I talk about logs. So I talk about the flowchart like this. So 10 here is your base, and then it's raised to the power of 1.3, and that's the answer to the right of the equals, is equal to this number in here, the 20, the number sitting next to the log. That's how I think of the flowchart whenever I do logs. So we tidied that up and we write log 20 is approximately equal to 1.3. The default is when we don't see a number there, it's base 10. For example, in maths, when we have 2x, the coefficient of x is 2. What about this one? What's the coefficient of x there? 1. We tend not to write 1x. It's just maths convention, and here's another one with logarithms. When it's base 10, we don't write the little 10 down there, so if you can't see a number, it's base 10, and you know that it's 10 to the power of 1.3 is equal to 20. So summarising what we have here, log of a is equal to b. Then what that means is, as I said, we've got base 10 here, this imaginary 10 down here. You have a little flowchart. 10 to the power of b must be equal to a. And so that's our equivalent. 10 to the power of what? 10 to the power of b must be equal to a. All right, so thinking about this, 10 to the power of what would be equal to 10? It would be to the power of 1. Log of 100 is, imagine this base 10 down here, 10 to the power of what? Here's the power over here, is equal to 100. The answer would be 2. And you see the pattern emerging. For 1,000, we'd have 3. If we think about writing this in a different way, instead of 10, 100, 1,000, let's convert these numbers all into base 10, and you'll see a pattern emerging, if you like. So the second one, instead of log of 100, let's call 100 10 squared. And the answer is 2. So you can see that when you have log of 10 to the power of a number, that answer is also the answer here, so that you can read off the power if you like. That's only if you get base 10 there. So that rule there is log of 10 to the power of something is the answer is also that power number. So on this screen here, we're basically trying to work out how this rule works down here. So the log of 34 is equal to 1.53. What does that mean? It's the little flowchart that I talked about. You've got base 10 down here, 10 to the power of 1.3, as we have written here, is equal to 34. Because the easy 10 that you know is 10 to the power of 1 is 10, 10 to the power of 2 is 100. So they're neat and tidy. But what if it's any other number in between of those powers? It's not so easy to work out. So this is where logs come in handy. And we can work out this rule here. So notice that if x is equal to 10 to the power of log x, well, what was log x back up here? So if we had 34, that was equal to 10 to the power of log 34. And what was log 34? That was 1.53. And so we can see that these are equivalent, that we've substituted in log of 34 for 1.53. Okay, doing some examples here, using our calculator to write in the form 10 to the power of x. So we're saying, what is x here? 10 to the power of what gives us 8? So if we can write it in the form of 10 to the power of log 8, we can see that the answer is going to be 8, based on the rule that we've established here. Using our calculators, log 8 is the equivalent of 0.903, and how many decimal places did it want? 4, so we have to cut it off there and round up to 3.1. So here, instead of log 8, we're going to put that as our power, and that was our answer for the first one. 800 now. Before we even do it, try and anticipate what the power will be. 10 to the power of 1 is 10. 10 to the power of 2 is 100. 800 is more than 100, so the power will be more than 2. What's the next one? 10 to the power of 3 is 1000. So that power there would be 3. So it's going to be between 2 and 3. Which one do you think it'll be closer to? Have a think. So you put log of 800 and work that out. And there you can see which one it was closer to 3. We rewrite that. 800 is equivalent to 10 to the power of log 800. And then the answer for log 800 is this, 2.9. So giving 10 to the power of 2.9031 is approximately equal to 800. Up until now, we've had no other way of working out what that would be for 10 to the power of. And this is where logs help us with that. 0.08, try and anticipate what the answer will be. 10 to the power of 1 gives you 10. Well, that number's less than 10. What's 10 to the power of 0? That gives you 1. This is still less than 1. So it's going to have to be a negative power, which means 1 on 10 to the power of 1, or 1 on 10 to the power of 2, which would be -1 or -2 as your power. Following the technique, work out the log of that number and notice it's a negative number as anticipated. Rewrite this 10 to the power of log of this, work out that, and that's your answer. And a couple examples here. I have skipped example 3 for time saving, and finding x such that log x is equal to 3. And how do we do that? So if we use the rule that we've got and we write 10 to the power of log x, and here we've got 10 to the power of 3, we get our answer like that. But I tell you what, the way I do that, when I see a question like this is how my brain goes. I imagine the base 10 there, and I do my little flow chart. 10 to the power of 3 is equal to x. So my brain goes 10 to the power of 3 is equal to x. However, you get in the habit of putting x on the left to solve, and that's how we get that 1000. How I do this next one, I'll put up the answer first, as in a different way of setting it out, and we get this answer here. I do my flow chart. There's a 10, base 10, so I say x is equal to 10 to the power of -0.271. Whenever you are answering these questions, it is absolutely fine to go from that line straight into this line, because it's showing that you understand that x is the power number that you were after. So thank you for bearing with us for that video, and next we look at logarithms in base A, so when it's not base 10, because we're heading towards base E, natural logarithms. Thank you.